So I'm just going to teach like this. And I think that it'll be nice because the projector's not shiny and light. But you can see, I think, my reflection of the ceiling. But so yesterday we did the basics of probability and we talked about mutually exclusive events. Today we're going to talk about non-mutual exclusive events, which are events that can happen at the same time. And then we're going to talk about independent events, which are things that are not related at all, two events that happen that aren't related. So what I'm going to do is we're starting at Roman numeral 4. So since you can't see the worksheet, I'm just going to write everything down. Roman numeral 4's title is non-mutual exclusive events. And you don't need to write this because it's already on your paper. So what we're going to do today is I'm going to go through these examples. And since I don't have to do a lot of drawing, I think that you should be able to follow along fine. There is a formula. If I say, what's the probability of this happening or this happening? There's a little formula, and the formula is I add up the probability of event A and event B. Then I know that this says or, but my last step of my little formula, how to find the probability properly, is I subtract the two of them and it has an and. So that's going to be both occurring. So if I say, what's the probability of this or this happening? I'm going to add the first probabilities. It's going to be a fraction, right? Add the second probability. It's going to be a fraction. Subtract. What about if they both happen at the same time? Okay. So here we go. A video game is played on a 34 by 20 rectangular. And a starship is represented by two overlapping circles. The radius of these circles is 6. The overlapping portion makes up 20%. Okay. Or 20 centimeters, sorry. And I want to know, the question is, a black hole will appear on the screen. What's the probability that it's going to appear inside my circles? So a black hole would just be whatever, a dot, I don't know. I want it to appear inside my circle. So, and what's the probability of that happening? I'm asking what percentage of my screen is covered up with my two circles. So this is going to be this circle or this circle. Either one is good with me. I want the black hole to appear in this circle or this circle. Okay. So I'm following along with this formula. If the radius is 6, that means that the area of the circle is pi 6 squared. And I want the black hole to be inside the circle. So this area formula is necessary because I want this space or this space. So probability is what is my desired outcome divided by total. The total is all the screen. This screen area is 20 by 34. That's 680 centimeters is the total. Okay. I'm going to do the probability of circle A, which is the area over the whole screen, the area of the first circle A, over the whole screen plus the probability of circle B plus pi r squared over the total screen, 680. Minus the probability of the combined. The combined is 20 centimeters. So again, my desired, the combined is 20 when they're together with the blue section. And the whole screen is 680. So I need a calculator for this. If you guys want to grab a calculator, you're going to need it. You're going to need a calculator at home because 36 pi divided by 680 is 0.166 20 divided by 680, 0.029. So I'm doing 0.166, and obviously I could have done more decimal places. Minus 0.029. 0.3. That's approximately what I got. And my question says, to the nearest whole percent. There's a 30% chance, which means 30% of my screen is covered up by the blue circles or by the black circles. So I had to find the area of circle A. And I divided it by the whole screen. I had to find the area of circle B divided by the whole screen. Desired outcome over total. Circle divided by the total screen. Then I subtracted, what if they both, where are they both in common? That's the blue section. That's 20 over 680. Okay. I hope you're keeping up with notes because I have to erase it to do the next problem. Next example is a card in a deck. Example 2. I'm going to leave my formula up because we're still going to use it. We haven't transitioned to the new, anything new. Okay. A card is randomly selected from a deck of 52 cards. Okay. Remember, in my deck of cards, I have 4 suits. Heart, diamond, spade, club. There are 52 cards total. How many in each suit? How many in each suit?
13.
13. So 13 of each suit. Okay, 13 hearts, 13 diamonds, 13, so you get it. Now, I've decided that I'm going to have my hearts be my A and the face cards. What is the probability that the card is a heart or a face? I want to know one or the other. And when I pick these cards, I'll be happy if I get a heart and I'll be happy if I get a face card. So how many hearts are in the deck? In a deck of cards, how many heart cards are there? So I don't even need to put P anymore. There's 13 hearts over 52 cards, right? So the probability of A, I want heart card. Plus, that's my formula. Probability of B, I want a face. Okay. Jacks have faces, queens have faces, kings have faces. So how many face cards are there?
Oh,
Because there's 4 of each suit, and then there's 4 queens, 4 jacks, and 4 queens, 4 kings, 4 jacks. 12. These are my faces. And there's 52 cards total. Now, subtraction sign. How many are both a face and a heart? A heart face. How many cards in the deck are heart and a face card? I know you know. Someone else in here on Zoom, you guys can talk to. On Zoom. Okay, well, he said 3. Do you agree with him? People on Zoom, hello. Wake up, respond. A face and a heart. How many cards in the deck have faces and it's a heart card? 3 is correct. He was right. So I'm gonna do 3 over 52. So this is an easy math problem. Took way longer than it needed to. There you have a common denominator. 13 plus 12, take away 3, right? 22 divided by 52. 11 over 26. If I wanted to know the percentage, I would divide. What's 11 divided by 26? It's like almost half. 13 is half.
0.42.
For what?
0.42.
42%. So this was example number 2 at the top of the page. I'm now moving on to example 3. Okay. So, of 162 students at an academic awards banquet, 48 won awards for mathematics and 78 won awards for English. 14 of these students won for both math and English. One of the 162 students is going to be chosen at random to be interviewed for the newspaper at the school. What is the probability that the student interviewed won an award for English or math? So it could be like the person that, not the person that did both awards. It's like, did you win an award for math or English? Just one award the person won, because only the 14 had the both award. So math is going to be, I'll make that A, and that's going to be 48 over a total amount, 162, right?
How would a question be worded if it wanted you, if it didn't care if they won both awards as well?
It would say, what is the probability that the student interviewed won an award for English and math? Or it would say the word both. This one says or, that last sentence in the paragraph says or.
No, I mean, if it
That's
was,
why.
I mean, if it was fine, if it said they could have won awards for, I'm sorry, I
That's fine.
read it.
That's fine. So the English people, I'll call them B, and that was only, or no, that was a lot, 78. Those English teachers, they give out all these awards. And both was only 14. So basically what I've done is I've set up your ratios that you need, because I'm going to do the probability of math plus the probability of English minus the probability of both award winners. So it's probability of math plus the probability of English minus the probability of the both winners, which was only 14 of them, remember? Yeah.
Would it be easier to just add or subtract the top numbers and then divide it by 162 after? And
Yeah.
do it?
You should totally 48 plus 7, okay. 48 over 162 plus 78 over 162 minus 14 over 162. Yeah, I changed them into decimals last problem. Let's do it a different method. Let's just focus on the numerators, 48 plus 78, take away 14, and divide at the end. Yeah. So what's that? 48 plus 78, take away 14. Someone on Zoom, please. Because these guys in here are awesome. They all know it. The question I'm asking is, can you please add? What's 48 plus 78, take away 14?
112 over 162.
Thank you. And what percentage is that if I cared?
Like 70%.
Yeah, it's like 70, just round it, yeah. That's fine. It's a lot of kids. 70% of the kids were award winners. Good. Okay. We're awesome. Doing good. So this formula, mutually, like things happening at the same time, events happening at the same time. Next, I'm talking about independent events. Independent is our next Roman numeral 5. That's going to be events, independent events, and that's going to be things that aren't even related. One thing is not dependent on the other. One thing can happen without knowing the result of another. Independent events. Independent events mean that I'm going to have one event does not affect the other event. This one has a formula as well. It's both events, and it's going to have the word "and" in the middle, and I multiply them. Okay. So now first we're going to do 3 examples where I'm just going to talk to you about before we start doing any math. Does this event affect the other event? So that would lead us to question number 1. A jar has 12 green and 8 violet marbles. A marble is chosen at random from the jar and replaced, put back. So I take a marble out of the jar, I look at it, oh, it's this color. I put it back in the jar. So now my second draw has all the original marbles in it. Does the color of the first marble affect the outcome of the second marble? So this is your logic in your brain. If I take a marble out, oh, it's green, but I put it back in, then I go to do my second draw. Does the first green marble affect my second draw? So yes or no? No, thank you, Jeff. No. The second draw, because I put the marble back, isn't affected by the first draw. Because I put the marble back. Obviously. Part B. A marble is chosen at random from the jar and not replaced. So I take it out. Let's say I choose a green one. Let's choose green. Does the color of the first marble chosen? So I'm going to choose green first. That's my first choice. So that means that I'm going to have originally the probability of me getting a green on my first draw There's 20 total, 12 of them are green. 12 over 20, which is 3 this. First draw, okay? Second draw will be over here. The probability of me getting a violet on my first draw, there's 8 violet, 20 total. Okay, so reduce that fraction, 2/5. Let's say first draw. I do not replace the green marble that I picked. So now on my second draw, there's only 19 marbles in the container, right? Probability of green on my second draw. Oh, what is this fraction going to be? Because I picked green first and then I did not replace it. I know, hold on. Zoom friends, hi. The second draw, I already picked a green. What's the probability of me getting a green on the second draw?
11 over 19.
Good job, because I took a green out already, and that means that there's only 11 greens left. And since there's a marble missing, there's only 19 marbles total. Probability of the violet, that doesn't change except for there's only 19 in the container. So I was just showing you how to write the probabilities. We still didn't like multiply or do any math yet. Turn the page, guys, turn the page. All right, the next problems are just yes, no questions, but you have to think about it. Can someone read, does it say example 4 on yours? The box cards? Okay, can someone read example 4 out loud for us? Ray, because you haven't helped yet. Go ahead.
There are 10 cards in a box, 5 black and 5 red. 2 cards are selected from the box one at a time. A card is chosen at random and then replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? Explain.
Okay, 5 black, 5 red. I pick the card and then I replace it. I put it back. Does my second choice affected by my first choice? I want you to be thinking about this at home in your head. I take a card out, but then I put it back in the deck, so I still have 10 cards. Is my second card pick affected by my first? Yes or no? Let me just call on someone at random. That's always fun, right? Just call your name, make you volunteer. Angela. On this question, is my second card choice affected by my first card choice?
Yes.
And then why?
Because the A and B are both included.
Well, I put the card, okay, I put the card back. I replaced it. So when I have my second pick, there's still 10 cards in the deck, like there was when I started. So if I put the card back and there's still 10, is the second choice affected?
No, because you put it back.
No, because I put it back. That's part A, okay? I replaced the card. I put it back. Part B says, a card now is chosen and not replaced. Then I pick another card. So I'm taking a card out. Now there's only 9 cards. And then I pick a second card. Does the color of the first card affect the second card? The color of the first card affects the possibilities of the second card. Ian?
Yeah.
Yes, you're right, because if I take out a card and I keep it and I don't put it back, that means there's less cards and there's less colors. Yes. Taking a card out affects the second choice. Okay, good, 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 good. All right, now we're gonna do some math. Finally, we call this example 5. Alex cannot decide which shirt to wear today. The probability of rain today is 40%. Okay, obviously these things have nothing to do with each other. So let me tell you actually her shirt choices because it's not listed. She has 2 yellows. She has 1 blue shirt. Let's just say they're all long sleeve because she thinks it's gonna rain. Okay, so here's my 2 events, totally crazy. My first event, my probability of my first event, A, is gonna be her picking a yellow shirt. What's my fraction? The amount that I want over the total of picking a yellow shirt. What fraction is that?
1/2.
Yeah, 2/4, 1/2 chance because there's 2 yellows and 4 shirts total. In case you need the written, there it is. And then it goes, the probability of rain is 40%. That's 2/5 chance. 40% chance. But listen, it says, part A, what is the probability that Alex chooses a yellow shirt? We got that. And that it does not rain. Oh, remember from day 1, you can go back if you need to, where I am subtracting an event because I don't want it to happen. So right now in this problem, if I'm saying, I know that the chance that it's gonna rain is 40%. What's the chance that it's not gonna rain? Well, that's 100 minus 1 minus 2/5. 1 minus 40%, right? Because if 40% says it will happen, what's the not going to happen? You just subtract it from 100%, right? So I'm going to actually multiply, check this out. 1 minus, I'll just say 2/5. You could say 40% if you want. When you're subtracting fractions like this, are you back in elementary school going, hey, this 1 should be a 5/5?
Yes.
What, am I doing something wrong?
Wouldn't it be 3/5? Because then then it doesn't rain in the.
Oh, it doesn't rain. Yeah. Well, hold on, I'll get there. 1/2 times 3/5. There it is, like that.
Yeah.
Yeah. Just multiply straight across, 3/10. 30% if I wanted to change it to a percent. Okay. And we'll just stop at part A. That's all. We're good. So I gave you a sample problems on Pearson. I'm going to add one to it right now. So let me stop recording.